Can you hear me now? Let me know if you can hear me now, because I see things that are jumping around over here. Okay. Okay, good. I have no idea what just happened. I've never had that problem before. Okay, and can you hear just one copy of me, or do you hear multiple copies of me? Because I think I muted the audio on the screen that I'm watching you all on, which is about 30 seconds behind. Okay, good. Okay, all right. So here's my plan today. I want to go through with you what happened in the test wizard, and I just want to share with you. There's two things that I noticed. I always, if I treat this like this would have been the test or even the review before the test, I have put questions on there that I planned that you probably would struggle with. So I feel like some of you felt like you came in prepared, and I'm sure you came in prepared. But there are a couple of questions that were on this assessment that, even if we were in a classroom and you saw me every single day, that we would be having the same exact conversations. Because there are many questions that are asked in this curriculum in terms of very specific things, and you could be saying beautiful chemistry, but you're not answering the question with what they're looking for. So there's a couple things that I definitely I need to go over with you. There's common mistakes that happen every year, whether it's in a classroom or not. So with that being said, I'm going to be bouncing back between the smart notebook so I can write on stuff. But what I want to show you is the actual back end of the test wizard, which is what I say. This is the grading program that I use. So I look at the question and I take a look at what's happening. They give me the correct answers that they would have accepted if it's in a Regents exam. And then I can flip through and I look at the response and I score it as either a 0 or I score it as a 1. So I'm looking for very specific things. And in this particular question, they want you to compare the rate of the forward reaction to the rate of the reverse reaction. And when you are asked about rate, so I'm going to go back over here for a minute. The key word here is the word rate. So if I had to highlight, I would highlight the word rate. And very specifically, the E in rate is what I'm looking at. The E in rate. Whenever I see rate, I'm thinking the rate of exchange with an E. Whoa, hey now. The rate of exchange with an E. Exchange. Rate of exchange with an E. And I am looking for a very specific word here. I'm looking for the word equal. Now, some of you are under the impression that the word equal necessarily means the same, and I can understand that, but there's a difference between when something is the same versus it is staying the same, and it's a very, very fine-tuned word that, phrasing that we look for here. I want you in the habit of whenever you see the word rate, I want you going rate and then going exchange, rate with an E, exchange with an E. I need to use the word equal with an E. The way that you will get points on this every single time is if I'm looking for the word equal, you use the word equal, you get points every single time, whereas if you start using the word the same, there's a difference between when you say something is the same, like it's equal to something else, versus it is staying the same, which would imply that it's remaining constant. So the word same is something that I refrain from using when I talk about rate. I want you using the word rate and using the word equal, because they're the two words that you're going to get points every time. And when you see the word concentration, I want you using the word constant. I never used the word the same, but the Regents exam will accept it as long as it is in the right context, which is the reason why they accepted here. They occur at the same rate. And that would imply in this wording, and you're going to see when the wording changes, staying the same versus it is the same. It's two different contexts. The other thing that I enjoy using about this task wizard is that when I score this as 0 or 1, it's going to list all the answers that I marked as wrong. And if I go through this, I can take a look here. They want to know why this is an equilibrium in terms of rate. And I'm looking at things here like the forward reaction is endothermic, the reverse reaction is exo, has nothing to do with the fact that it's in equilibrium. Those are true statements, but not what they are asking you. And the forward reaction is endo. Actually, the forward reaction here is exo. So this is a matter of wrong statement, but at the same time, it could be in correct context where you're saying something true, but you're not answering the question. The rate of the forward and reverse decreases. No, they have to be set equal to each other. They could both be decreasing equally, but that's not what they're asking you. Someone said the forward reaction is not being used. The rate of the forward is slower than the rate of the reverse. All of those things are, they're not achieving an equilibrium if the rates are not equal to each other. Somebody said here the forward is exothermic. Like, that's a true statement. Forward is exothermic, but it has nothing to do with the rate of the forward versus the rate of the reaction going in reverse. You're not answering the question. The rate of the forward reaction, the rate of the reverse reaction is constant. Constant would mean that the rates are staying the same, but it doesn't necessarily mean the rates are equal to each other. And that is really important, that the rates of exchange are equal. And I go back to that little story of the school bus where two people get on, two people get off. The fact that two people got on is equal to the fact that two people got off. That is what we refer to as equal. Where constant would just mean that the values are staying the same. It doesn't necessarily mean that they're set equal to each other. So I really like using this test wizard program because it shows me the common mistakes that are made. And if I look at this, there's really no way to get around this answer that we're looking for them to be the same, or we're looking for those rates to be equal. Take a minute, give me a thumbs up on the sidebar before I head to the next question. Let me know if there's anything you want me to address in number 1. Okay, I'm moving on. All right, number 2. Number 2 says, describe how the catalyst zymase speeds up this reaction. So I'm actually going to go to the Smart Notebook file for a minute, and I'm going to take a look at this. If this was the chemical reaction, I don't know if this is actually your endo versus exo. Doesn't really matter. Let's say that this is an exothermic process. This is my artistic sketch of an exothermic diagram. If I were to add a catalyst, the catalyst is going to provide an alternative pathway. So when I provide that alternative pathway, it is going to make it easier to activate this chemical reaction. This very, very specific green arrow is what we refer to as the activation energy. So a lot of people who got this question wrong, they said it takes less energy in order to perform this reaction. Like, yes, but kind of like no, because the delta H, which is the heat of reaction or the overall energy change that occurs in this reaction, the heat of reaction actually stays the same. So you're not changing the heat of reaction. What you're doing is you're changing the amount of energy it takes to activate the chemical reaction. So when I looked at this question, I was looking for a few different things here. I was looking for you to talk very specifically about the activation energy, or if you don't talk about the activation energy, you talk about some sort of alternative pathway to activation. You're talking about this alternative pathway. This is a phrase that I have never used in class. It changes the reaction mechanism, which is extremely high-end chemistry, which is something we don't talk about in this class. So you can imagine my surprise that as I was grading some of these and I look at the correct answers, I started to see people who used the phrase, it changes the reaction mechanism. And I saw it more than once. Like I saw a couple people use that phrase. It changes the reaction mechanism. Now, I look at some of these and I take a look and, you know, I feel like it's really, really, just give me 30 seconds and check the caller ID. Hold on a second. Okay, so I take a look at this and I see phrases that are exactly from the Regents answer key, and I understand that these questions are posted on the website and sometimes there's no other way to see something, so it doesn't surprise me, you know, like some of you wrote, oh, it provides an alternative pathway, like, oh, it lowers the activation energy. Those are phrases that I feel like I drilled in your brain that you should be using, but I never used the word changes the reaction mechanism, and I honored it because it was on the key and technically it's correct, and I would take that if it was a Regents exam, but at the same time, you know, I don't know where that phrase would have come from unless this was actually looked up on the internet, because all of these questions you can find on the internet. You need to understand that the way this online grading system is working right now, it's about completion, and I would rather you give me an answer that's wrong so that we can like talk about it and we can understand why you don't understand something than for me to just read the answer that's, you know, written on the that is written on the answer key from the state's website. So with that being said, please, 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 please just give me your best effort. If I were to take a look at some of these answers, like they're worded word for word from the state answer key, so it's kind of like not helpful for you. Like it doesn't help you because you don't know the answers, and I want to be able to fix you, but at the same time, it's like, you know, wasting my time that I'm grading the state answer key because it's not your work. I'd rather you make a massive mistake that we can talk about this than anything else. If I were to take a look at the most common mistakes, so common mistakes on this one, the catalyst, it's a catalyst, so it requires less energy. I feel like that this is this answer over here, but you didn't talk about the alternative pathway, so I did not give you credit on that. Some of you said it decreases the amount of energy that's needed. Like, yes, the amount of activation energy, you have to use a very specific adjective before that, the amount of energy it takes to activate, as opposed to the heat of reaction. That's another form of energy in this reaction. You were not specific enough, so I did not honor that if you just talked about it used less energy. That's really where a lot of you lost points here. Catalysts have nothing to do with surface area, has nothing to do with the fermentation process. It requires less energy. Like I'm looking for very specifically the word activation energy here if you're not talking about the alternative pathway. So that's why people lost points on the second one, and I think a lot of you understood maybe the concept in theory when we were learning about it, but it was your execution of answering the question that you did not either address the alternative pathway or you did not handle the other component, which is talking about the activation energy. I wanted those two things to be in there for your answer. Give me a thumbs up to make sure we're on the same page, because I'm moving on to number 3. Okay, give me a thumbs up to make sure we're good. Okay, moving on to number 3. State evidence from the equation that the forward reaction is exothermic. So I'm going to head one more time into my Smart Notebook file, looking at question number 3. If I cut this reaction in half, the energy term is a product. So things I would have accepted here. The energy is produced. The energy is a product. The heat is on the right-hand side. I wanted a piece of evidence that was clearly from this equation, because it says from the equation that this is exothermic. So it's a little bit of a stretch for you to say that, oh, the heat is released. And depending on how you worded that, I ended up taking that only because I feel like it is, you know, it's a true statement, but is it necessarily happening in the equation, and that's how this is worded. State evidence from the equation. So you have to make sure that you are addressing the evidence in the equation instead of just, saying true chemistry. That's not appropriate to the equation that they're giving you. So let's just take a look really quick at things I accepted. Heat is on the right hand side. Energy is being released. There's for its exothermic because you're talking about the releasing process. Energy is released there. Okay, so I'm taking most of the time that, energy is being released, even though, it's not directly from the equation. It's a little bit of a stretch. And I think the day of a Regents exam, they might hold you a little bit more accountable. But at the same time, I took that from you because many of you did not go that extra mile and talk about it specifically in the equation. If I were to take a look at some things that were that I did not accept here, the forward reaction is exothermic because heat is being added to the other side. If you use the word add, you are implying that it's being absorbed. You want to use the word that it's being released, and that's definitely a different word than adding. This word adding throws this off. The forward reaction is 58 kilojoules. That's true, but where are those 58 kilojoules located? Are they located on the right side? Are they located on the left side? Where are they located? That makes a massive difference. The forward reaction is endothermic. No, it's not. If it's endo, it would be on the other side because you'd have to use it in order to get it started. The reaction is exothermic because you are releasing, therefore more products than reactants. Like I don't see that here. I have one reactant, I have one product. Maybe the moles are different, but I'm not getting this here is throwing me off in terms of being able for me to accept that answer. Okay, the other wrong answer that I got going on here has something to do with entropy, and that has nothing to do here with the fact that this is exothermic. Okay, exothermic is talking about the energy being released or the energy, the energy being a product for the most part. I accepted almost everything, but the only thing I need to say here is that if you ended up just writing here, energy is released, I probably, if this was in a classroom and I had, I was reviewing this, I would say to you that, the day before the test, it has to be explicitly from this equation, and I'm not seeing this word released in here. I want the evidence in this equation that's telling me that this is being released. I was a little bit on the generous side with number 3. Give me a thumbs up to make sure we're in a good place. And I'm moving on to number 4. Hi, Mason. I think we're all good. Okay. Question number 4. State one change in reaction conditions other than adding a catalyst that would increase the rate of this reaction. So things I would have accepted here. I would have accepted increase the surface area of the zinc. I'd accept that, because the zinc is a solid. Increase the temperature of the reaction, I would agree with that here. If you increase the temperature, there's more movement. That would increase the rate. Use a more concentrated HCl solution, I would accept that too. The only things that I really did not accept in here were talking about pressure, because in order for you to increase this rate of reaction, like we're talking going forward, like it's a forward reaction, I don't have gases on this side. So pressure is going to have nothing to do with me trying to, speed this up. Things that I did not accept here, closing the test tube, well, that's true if there's a gas on the reactant side, it's not going to speed up the rate of reaction. Other things people wrote here, to change the temperature. Well, yes, but what if you change the temperature and you decrease the temperature? Would that increase the rate of reaction? These answers over here, I did not accept because you are not specific in your temperature change. And the whole thing with sealing the test tube, that would work if the gas was on the reactant side. It's not. It's a product, so I didn't accept that here either. Give me a thumbs up on number 4. Anything you want me to address? Otherwise, I'm moving on to number 5. Tyler, you can just say the word thumbs up. Give me a smiley face. You can pick a different finger, whatever. You can give me like a high five, whatever you want. Just let me know that we're good and you're ready to move on and you don't have any questions you want me to address. Okay. Nice. I like that emoji, Tyler. Awesome. Okay, number 5. Explain why this reaction will not reach equilibrium. So, there are things that I accepted that are clearly on the key, and then there's things that I accepted that were not on the key. And then there was something on the key that I had a little bit of a hard time accepting, and, it's one of these things where I feel like they might take it the day of a Regents exam and it's a little bit more of like a pity point kind of thing, but at the same time, I was not in love with the answer because they feel like you didn't explain it the way that explain it enough that I understood that you understood what you were trying to say. And again, I feel like a lot of this is it's wording directly from the answer key. So I was looking for you to talk about this is not going to reach equilibrium. And if you read carefully, they're telling you that this isn't an open test tube. And that wouldn't matter if all you had was a solid and aqueous. But the fact that you're producing a gas and this is an open test tube, this reaction will never reach equilibrium because the gas is going to escape from the open test tube. So things that I accepted, let me find in ones I accepted. So things I accepted, it's an open test tube. You can't reach it because it's open. The gas will evaporate. You'll not reach equilibrium because the test tube is open. For the most part, I was looking here that it's not a closed system. The test tube was open. You're producing a gas. The gas can escape. There are things that I was taking a look at when people got this question wrong. A reaction didn't take place. A reaction did take place. Okay, energy is being added to the products has nothing to do with the energy term. The reaction is not reversible. And I feel like if you look at this, like there's a one-sided arrow here, which may imply to you like this reaction is not reversible. But my question to you is like, why? Like, why? Why is this not reversible? Like, why can this not reach equilibrium? Because you're producing a gas and the gas is escaping. So I went back and forth on this one, and I feel like this particular answer choice, if it was the day of a Regents, they're going to take it from you. I'll be honest. If this was my exam in class, I would feel like you didn't demonstrate to me a sufficient understanding. I feel like I hold you sometimes to a higher standard so that, the day of a Regents exam, you nail it and you're able to explain what it is exactly that you're trying to say. I was not in love with this reaction as reversible because you're not telling me why it's not reversible. You're not telling me why it did not achieve equilibrium. I know that this is technically on the key, but I'm giving you my reason why I did not take it on this particular assessment because I want you to have that understanding that this is producing a gas and there was an open test tube and that gas is leaving. So, for the most part, I feel like people, there was very few people, enough of you said that it's not reversible. Enough of you said it was not reversible. But for the most part, I feel like people who did not get this question right, it wasn't a matter of that, so much as that they were saying things that were just not true in the first place. Take a minute and ask me if you understand, you're wrapping your mind around this question, because I think that this was one of the most missed. This was a big group of people who did not get this question right. Okay, I'm going to move on to number 6. I'm just going to wait for you to give me some sort of yay or nay. Make sure we're on the same page. Okay, so I honestly think that number 6 may be one of the hardest questions. No, that's not a lie. That's a lie. There was another one. This is not the one I'm thinking. Question number 6 says, explain in terms of collisions why increasing the surface area of hot carbon increases the rate of the forward reaction. You have to talk about collisions in your answer. So if I were to go through the answer choices or the answers that I accepted, they all talked about collisions, or they're talking about this I should not have taken. Collisions, collisions, collisions. They're all talking about collisions because this question is clear as day saying in terms of collisions. If I go back and take a look at the things that I did not accept, it's not to say that you are not saying true statements, but you're not answering the question because you're not talking about a higher frequency of collisions because there are more surfaces to collide with. Some of you did talk about collisions, but you're saying that you're lowering the energy needed for a collision. That's not true. Like, you're still going to need the same amount of energy. It's just that there are more surfaces to collide with. So if I were to look at answers that people got wrong here, it's a matter of they're not talking about collisions. And if they do talk about collisions, they're not talking about them in the correct context. So moving on to number 7. State in terms of rate of forward reaction and reverse reaction. Number 7 is actually just like number 1. I was looking for the word equal. Or they are equal, or the rates are the same as opposed to staying the same. That's a very different phrasing. If I were to take a look at things that people got wrong on number 7, they're saying that it's happening at different rates. It's saying something about the heat. I feel like if you didn't get question number 1 right, you did not get question number 7 right. And I actually meant to take one of them off, so it wasn't like a double jeopardy thing. But at the same time, you know, it's one of these things where you have to talk about the fact that the rates are equal. Somebody said the moles are equal. It has nothing to do with moles. Like, this is not a gas problem. We are talking about a Le Chatelier shift. The rate of exchange here is equal, and you had to specifically say the rate was equal. Okay, number 8. I'm going to pause for a minute on number 8. I'm going to wait for the video to catch up. Just give me yays or nays or things you are not wrapping your mind around to make sure that we are on the same page. There's no questions. I'm going to be hitting number 8 in a minute. Okay, I'm actually going to head to the Smart Notebook file for question number 8. So number 8, okay, they want you to state the effect on the concentration of the ClO minus when there is a decrease in OH concentration. So I'm going to cut this reaction in half, and this achieved equilibrium. We had a double-sided arrow. The rate of exchange is equal. The concentrations are constant. Le Chatelier says, happy, 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 equilibrium. And then all of a sudden, Le Chatelier comes along and goes, oops, I shattered on the freaking system. I just changed the amount of OH minus. They want to know how the chlorate is going to be affected. If there is less hydroxide, I'm going to start doing this shift. Less hydroxide means I cannot produce as many products, which means I will have excess chlorine lying around. I want the effect of this change. I specifically want to know how is this guy being affected. All I was looking for is that the concentration of Cl ion decreases. The Cl ion decreases. I have less ClO minus ion than I started with. And if I take a look at what people got right or wrong on this, people were talking about completely other things. Like, oh, the water will decrease. Some people talked about the actual shift. And I get it. You said something beautiful, but you didn't answer the question I needed to know about the concentration of ClO minus. You're talking about a Le Chatelier shift. That is a related concept, but it is not the answer that they're looking for. Something went wrong here. You said Cl ion is decreasing, but you said it when OH minus is increasing. That's not what they're saying here. You're decreasing the OH minus concentration. So sometimes it's just a matter of wording. And again, I saw so many people talking about shifts. Like, it's a beautiful thing. You're talking about true things in chemistry, but you're not answering the question the way that they want it. Okay, Olivia wants me to go back to number 6. So I'm going to go back a second. Explain in terms of collisions why increasing the surface area for hot carbon increases the rate of the forward reaction. So Olivia, I'm going to go back and look at number 6. Right now you have solid carbon. So that's like taking a chunk of carbon and you're going to react it with water, and you're going to produce these two things. Well, that's a hideous looking star. A star, and we'll go black on this one. These products over here. Now, what you're doing when in order for this to happen, you have to have a collision between red and blue, produces star and heart. But what they're saying in this question is you're going to take this chunk of this red hot carbon, which is in the solid form, and instead of leaving it as one giant chunk, you're going to split that up into many, 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 many smaller pieces and particles. If there are more smaller pieces and particles, these smaller pieces and particles will have a higher likelihood of individually colliding with that blue circle. If I got one chunk, what is the likelihood that this chunk is going to hit that blue circle? Like there's, it's like one chunk and one blue circle. Instead, I have, like 100 smaller pieces. What is the likelihood that one of those 100 smaller pieces is going to hit that blue chunk? A whole lot higher, because I have more surfaces to collide with. I had to very specifically talk about the fact that there are more collisions possible when I have more surfaces to collide with instead of leaving it as one giant piece. Olivia, give me the thumbs up that I answered this for you. I'm going to move on to question number 9. Just give me the thumbs up on 8 and 6. Olivia, you personally are 6. Everyone else give me a thumbs up on 8. And I'm going to head into question number 9. Okay. So, question number 9. Let's look at this in the test wizard. Oh no. Okay, give me 1 second. Okay, question number 9. Okay, so in this question, they want you to state in terms of concentration. And I want evidence that the concentration has reached equilibrium. And the key word for concentration here is that the concentration needs to remain constant. So concentration stays constant. Now here's the kicker. If you said that the concentrations are equal, the concentrations are the same, they are not the same. Like if I look at this picture, this concentration is about 0.75 for reactant, and it's about 0.01, 0.075, 0.01 for product. The concentrations are remaining the same. They are staying constant. That's why I like to use the word constant and never use the word the same. Because if you say they are the same, they are not the same. The word the same by itself implies that they're equal. If you say they are staying the same, it implies that they could be different values, but their values are staying constant. That is the reason why I never use the word the same here. From day one, I have used the word equal, and I have used the word equal for rate, and I have used the word concentration and constant together. This question, clear as day, is using the word concentration, and I am looking for you to say the word constant. And I'm looking here, things I accepted. Constant, 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 constant. It is staying unchanging. That's another way of saying constant. If I accepted if you use the word the same, you had to say that the reactants are staying the same. They stay the same. They are not the same as each other, and that's where people lost points. I'm going to look for no point here. The rate is the same. Well, I'm not talking about rate. I'm talking about concentration. The concentration is at the same levels. No, they are not. The concentrations are not at the same value. They are remaining the same as what they were, but they're not set equal to each other. So the reason why people lost points on this is because they used the word equal, or they said it is the same instead of saying they are the same. It's the reason why I never use the word the same. So give me a thumbs up on 9. I'm moving on to number 10. And with number 10, I am going to compare number 10 to, I believe it's number 8. 8? Number 6. Okay, number 6, clear as day, is saying to you in terms of collision. So you gotta talk about collisions. Whereas in question number 10, they're saying to you clear as day in terms of Le Chatelier's principle. So I'm gonna head to number 10 in my Smart Notebook file. And I'm gonna need to shrink this down. In my Smart Notebook file, in terms of I didn't mean to cross it out. In terms of Le Chatelier's principle, there are 2 answers that you can go with. And the answer is shift to the left or shift to the right. This will get you points every time. You got to pick one or the other. And the reality is, even if you don't know the answer, okay, Olivia, I'm going to come back really quick to your question on that last one. And I'll tell you why that was not okay. In this particular question, your answers are either shift left or shift right. It is one or the other. Like, you got to pick one or the other. And you got a 50-50 chance of getting it right, even if you don't know what you're doing, if they say to you in terms of Le Chatelier's principle. They want to know in terms of Le Chatelier's principle why the final concentration of NH3 is greater than the initial concentration of NH3. So, if I go back here, I am adding H2 to the system. So, cut the reaction. I have more H2. I will produce more ammonia. I will have less nitrogen because I consumed it in the process. If I were to evaluate this in terms of the shift, I would be shifting to the right. And the right answer here that I was looking for is to the right. There are other ways to say this. If you shift to the right, you are favoring the forward reaction, but you don't even need to say that. All you need to do is say left or right. If you are going to say, oh, I am shifting to the left, you have to very specifically say, if you want to get specific here, that you're favoring the reverse. You don't need to do that. You can get away with saying left or right and be done. If I go back and I take a look at things that people got right or they got wrong, taking a look here, the right answer is shift to the right. The reasons why people got this wrong is they were talking about other things that had nothing to do with shifting to the right or shifting to the left, or talking about the fact, shift to the right. This is right. I don't know who that is, but I owe you a point. Okay, I owe this person a point, and I'm not going to go through and show names right now to figure out who that is, but I owe this individual a point, and I promise you that I will get you that point back. I'm very specifically looking for you to say shift left or shift right, and in this question, we're shifting to the right, which means we would be favoring the forward reaction. Okay, Olivia, your question said oh, okay, good. You're good. Olivia, the reason why I could not accept your answer is because they were specifically talking about concentration. They were not talking about rate. Okay, you use the word rate, and they are clear as day using the word concentration. Okay, I'm moving on to number 11. I think number 11 is the hardest question on this entire assessment. And to be honest with you, if I had to rank all the questions in terms of difficulty on a Regents exam, I think that this is actually the number 2 stunner. It's difficult. It's actually number 2 or number 3. Number 1 and number 2, like the first 3, this is one of the top 3. The other 2 really difficult questions are in another unit called redox, which happens, sooner than later. It's coming. But I think that this could possibly be one of the hardest questions that you have to answer so far this year in terms of the Regents level curriculum. I'm going to head to number 11. Okay, let me shrink this down. here's the equation. I'm going to cut this reaction in half. Explain in terms of collision theory why the concentration of O2 decreases when more H2 is added. So let's do the shift. If there's more H2, there's more ammonia, which means we have less nitrogen. This question is saying to you why, and you have to talk about collisions. Let's draw for a minute. Let's say you had 1, 2, 3, 4, 5 pieces of nitrogen, and you had 1, 2, 3, 4, 5 pieces of hydrogen. Let's go a few more. Let's lie. 1, 2, 3, 4, 5. And we are producing ammonia, which is, let's go red. 1, 2, 3, 4. Let's go 2, because that's what the mole ratio is. And this right now is achieving an equilibrium. It can be reversed so that these concentrations stay constant. The rate of exchange is equal. Fine. All of a sudden, somebody comes along and they Lachat on the system. We're going to add more H2. I'm going to start dumping in more H2. Take a step back. Every time a chemical reaction happens, there has to be a collision between, ungroup, there has to be a collision between a blue and a green. Blue and green need to collide together, and when they do, they produce a red. But at the same time, a red can be broken back down. In order for you to make a red, you need to have a blue and a green collide. And this achieved an equilibrium. All of a sudden, someone came along and they dumped more green into this system. If there is more green, there is a higher chance, I gotta ungroup this, there is a higher chance that green and blue can meet in more frequency, which means every time blue and green meet and have this perfect collision, they get converted into red. These guys collided, and they are now product. When I added more of this hydrogen to the system, there were more collisions that happened between the nitrogens, which are blue, and the green hydrogens, which produced more product. In terms of collisions, when I have more H2, there are more collisions that exist between H2 and N2, producing ammonia. When there are more collisions, that's fantastic. You have to then seal the deal here, which is the reason why this is the hardest question on this entire assessment. You got to talk about why H2 begins to decrease. When there are more collisions, this nitrogen is going to be consumed to produce more product. If this was a classroom exam, I guarantee you that many more of you would have been getting this question wrong. If I were to look at the answers here and the way that this is worded, adding H2 causes more collisions, more reacts, reducing this concentration, more collisions, the H2 is used up. If I look at right answers, some of these wordings are exactly what the Regents answer key provided. Some of these are word for word from the Regents answer key. And if this was a test in class, I don't believe I would have gotten the number of word for word answers that showed up. Like this one over here. Like, that's pretty much word for word, even with the phases in it. It's word for word. Like even down to the therefore. So a lot of the people who got this question right, if I were to take a look, I feel like if this was a test that happened in class, I feel like there would be people who wouldn't be getting this question right because for whatever reason, I'm not going to make any inferences here, but for whatever reason, the answers that were on the state website found their way into your answer word for word. And I really would challenge you, if you got this question right, but you don't understand why, you just, lifted the answer from somewhere else, you really should go back and you should be able to figure out why this happened, because it's one thing for you to get it right in the test wizard, but it's a very different thing for you to understand what it is that you got right or wrong. I want you to take a minute and give me a thumbs up, thumbs down. I'm going to be wrapping this up like in the next few minutes because I think that that was one of the harder questions. And I want to get through the rest of this and call it a night. Give me a thumbs up, thumbs down. Okay, moving on to number 12. Explain in terms of particle arrangement. So you have to talk about the particles and their arrangement. Why the entropy of water decreases when water freezes. Most popular wrong answer here is people talked about water particles expanding. That's a true statement, but it has nothing to do with entropy and the particles arrangement. Entropy is about the amount of chaos and disorder. So you have to talk about the fact that when you become a solid, the particles are becoming more ordered. Things that people wrote here, you talked about particles expanding, but you didn't talk about the entropy. Or people just wrote it becomes a solid without talking about the particles arrangement. Clearly, if you wrote it's becoming a solid, or you're saying water is more random, you're not talking about the particles arrangement. You had to very specifically say that solids have a more ordered arrangement of particles, where liquids, if you talked about the liquid being less chaotic, or I'm sorry, more chaotic, you had to talk about the fact that the particles are arranged in a more disordered way. People who got this question wrong, it's because you are not talking about the particles in the correct context. You're not talking about particles. Many people said, oh, it freezes. This one I owe this person a point. When water freezes into a solid, the particles become less random and compact. This person is owed a point too. When I was looking for right answers here, I was looking for you to talk about particles and their arrangements. Okay, question number 13. State how the equilibrium shifts when SO3 is removed from the system. I am looking very, very specifically for you to talk about a specific side. So they're saying to you here that, you're talking about the right. You shift to the right, and if you're shifting to the right, then I would have accepted here that you were talking about you're favoring the forward reaction. I am looking very specifically here for a directionality. We're shifting forward, we're going to shift forward, or I'm looking for shift to the right, or you're talking about the fact that the concentration of reactant is going up. If I look at what people got wrong here, they were not talking about a directionality. Okay, moving on to question number 14. Based on table I, explain why there is a decrease in temperature when KNO3 was first dissolved in water. And your clear giveaway here is they're telling you to go to table I. So let's actually do that. Let's type in chemistry reference table, Regents chemistry reference table. And let's do table I. Let's get an image. Table I. Table I? Table I? Those are all table F. I want table I. I have to open up the whole reference table. There it is. Table I. And let's snip you in. Snip. Okay. And I think this is number 14. Yep. Okay. Okay. They're telling you clear as day that this is reference table I. And what I recommend you would do here is find the equation that they're telling you about. They're telling you that this is KNO3 and it's dissolving. So if I'm a highlighter and I look for KNO3 dissolving, that's this guy right here. The value is a positive delta H. So positive delta H value, positive delta H, positive 34. If this is positive, that means it is endothermic. And all I'm looking for here right now, because it's based on table I, that it is an endothermic process. I would accept that. Or I would accept that you had to absorb energy in order to do this. And when you absorb the energy, it has to come from somewhere, and that's the reason why the temperature is decreasing in the environment, because this dissolving process is absorbing energy. I am very specifically looking for you to talk about a positive value. I'm looking for you to say that, oh, energy is being absorbed. And some of you are like, I didn't even know that that like was a thing, positive or negative. If you read the bottom of the table, they're telling you that a negative is exothermic, which means if you got a positive, that means that you have something endo. Give me a minute, give me a thumbs up on the sidebar to let me know we're ready to move on to the next question. Okay. State what is represented by interval A in the potential energy diagram. It's the heat of reaction. So things I would have accepted here is heat of reaction. I would have accepted from you here the delta H value. That would have been acceptable too. I would have accepted the word enthalpy because enthalpy is the official scientific name. For this, the most popular wrong answer for number 15, people put product or they put reactant. And I can understand why people would say, oh, that's reactant. Because it's like on the reactant-y looking line. Like it's like, you know, right, it's like in this reactant area, but it's about the span that arrow is, you know, spanning, and what you're labeling is you're labeling the difference between the reactants and the products. So if I look at what people got said right or wrong here, people either put the word reactant, they put the word product, it's about that distance. The other really popular answer here was exothermic because it's going from high to low, but you're not answering the question. They want you to label what A is. The right answer here was the heat of reaction. Okay. Okay, question number 16 is pretty much just like what happened with question number 12, but instead of 12, they're very specifically talking about the particles arrangement. Whereas in number 16, they didn't give you that stipulation. So you could just say, when you use the word compare, all I needed you to say when you talk about the word compare, you have to say which one is more, which one is less, or you have to say that they are equal to each other. If you say more, you have to tell me which one is more. If you say less, you have to say which one is less. And if I were to take a look at where people lost points here, it's because you're saying, oh, it's increasing. Like you're not specific enough for me to know which one you are talking about. Like, which one has a higher entropy, which one has a lower entropy. You're not specific enough in your answer for me to clearly identify. When you say the word compare and you say this one is higher, you have to specify which one it is that you're talking about. If you're saying this one's lower, you have to specify which one it is that you're talking about. Okay, thumbs up, thumbs down. I'm moving on to number 17. What is the activation energy for the forward reaction here? Okay, if you're going forward and you're activating, you have to start from the activation point. So I'm going to go to question number 17 on here. Question 17. I need to activate. So I'm going to activate with the catalyst, which is the dotted line. So the most popular wrong answer is 140. And I get it. I understand why people think this is 140. But you got to understand that you started at 40. And the activation energy is how much energy it took for you to activate from the starting point. If you start at 40, you activate to 140. The right answer here should be 100. Most popular wrong answer, if I start flipping through, if I look at wrong answers here, 140, 140. Some people just put 40. I don't know where 40 came from. But 140, 140, 140. Some things I got was 20 and 80. I think that's just a matter of you didn't know how to read the diagram. I think the 80 came from subtracting the heat of reaction, which is the next question. What is the heat of reaction? The heat of reaction, I'm going to jump to the Smart Notebook file. Okay, the heat of reaction is the distance between these two lines. So that's where this 80 is coming from. If I subtract these two, that gives me my 80. And wrong answers. Yeah. Yep. I just think it's, you don't know. The heat of reaction is the distance between the two flat lines. Okay, number 19. This is actually a mole ratio question, which is math of chemistry. It was a great review moment. If you have 622 kilojoules and that's what's being absorbed, okay, I am going to set this up math chem style. Like, this is my recipe. My recipe calls for 227.4. I don't need 227.4. I need 680.2. 682.2. They want to know how many moles of this I'm going to need, so I'm going to cross multiply. So that is like 227.4x equals 682.2, and there's a 1 here. It's implied there's a 1 because this is balanced and there's nothing written, so times 1. I would just solve for x and isolate my variable. Give me the thumbs up on that one, and let's head to the last question. Letter B represents which chemical formula or formulas in the equation? This is another one of these scenarios where I feel like you know things, but you don't answer the question. You have to talk about the formulas in the equation. You gotta talk about this equation. And if we look at letter B is product in the forward reaction, and you had to identify this is the this is it. This guy right here, or you had to say C2H2. If I look at the most popular wrong answers, product, close. Product. Oh, everyone writes wait. It had to be about the formula in this equation. You had to identify the product. So that's another one of these things where I feel like so many people, you understood what you were talking about, but you didn't answer the question. That is pretty much it for tonight, going through everything that, we had on this assignment. If there's anything that you want me to go over still that you don't understand, shoot me a text and a remind. Otherwise, I'm calling it a night. I need to put together some stuff heading into new content for you, so check the website tomorrow. I will be posting the assignments for tomorrow, what you should be working on. I know that something came out with a schedule that I have to take a look at and see how I'm going to be working that schedule into whatever it is that I'm doing for all of you, because I don't know if I can be live in the times that were listed for science, because there's 3 small people who will die if I'm not watching them actively all day long, and I don't know if I can be live to stream during those times. But what may end up happening is that I will still stream live at night, and you can choose to watch it as I would be taping whatever it is that I'm going to then be posting not live. And if you want to watch what I'm doing live, and ask questions as I'm doing it, I'm totally fine with that. But then I would just be posting those assignments to be done in whatever window it is that they're giving me. I don't know if I can be live in that time frame that they've listed. So I will get back to you on that and figure out how that's going to be handled. Otherwise, I will be starting new material with you tomorrow. I got things for you to read and some videos for you to watch before I stream. So have a wonderful night. Give me a thumbs up. Let me know we're good. I miss you all, and I will see you all soon.